So, welcome everyone to the latest in the monthly seminar series of Spatial ML, the EPSRC International Centre for Spatial Computational Learning. I'm really excited to have Mike Hutton here from Google. Known Mike for a number of years. Mike received his BMath in computer science in 1989 and his MMath in computer science in 1991, both from the University of Waterloo, and then his PhD in computer science in 1997 from the University of Toronto. Across 20 years at Altera, Tabula, and Intel, he worked on FPGA architectures, on CAD and applications. He's the author of 30 published papers and over 100 US patents in these areas. He's served on multiple FPGA and CAD program committees. He's a former associate editor of IEEE Transactions on VLSI. And in 2018, he joined Google, where he's focused on architecture and performance modeling for the tensor processor architecture. So really pleased to have you here, Mike, and please take it away.
Thanks, George. So I'm going to talk today about the TPU version 4 for about half of the time, and then about half of the time going into other trends in machine learning hardware that lead to generations after that. So first of all, the TPU V4. So this is a 7-nanometer chip. It's not the most recent TPU, but it's the most recent one that I'm allowed to talk about. I put a note at the bottom. TPU V5 was recently announced at Cloud Next about 2 weeks ago, and that's now in production, but I'm not going to talk about the details of that today. There are some details on the website if you want to look. The TPU V4 is primarily optimized for training. There's a companion chip, the TPU V4i, which is a single-core device aimed at inference. The training chip has 2 tensor cores, 4 HBMs, and it's connected in a 3D Taurus. And one of the things I'm going to spend a fair bit of time on is talking about the interconnection network. So there'll be some slides on that later. In terms of basic raw stats, it's got 275 peak teraflops of BF16. It also supports int8, but in this generation doesn't give you any particular advantage of int8 other than in memory bandwidth, because the flops, there's no special purpose hardware for int8 flops. Typical power is about 200 watts. This is the guarantee that we give to the people in the data center that they can use at least the typical power and beyond in order to make sure that we can hit our SLOs and not throttle, especially with inference, but also with training. People care to not be throttled because then they get predictable runtime. More so with inference, but definitely with training. More so with inference, but with training as well. The chip is water cooled. That's because we can, because we own the data centers and do everything from bottom to top. We can choose to do water cooling and things like that. That would be more difficult for a commercial product to do. Here's a block diagram. There are 2 tensor cores shown in blue up at the top. Sorry, let me turn my laser pointer on. 2 tensor cores, first one here, second one here, process the main bulk of the computation. There's a common memory, 128 megabytes of common memory that is used between the 2 tensor cores. In addition, they have their own vector memory of 16 megabytes. Each of the tensor cores has 4 multiplier units, so we can do 4 parallel multiplies. And the compiler basically schedules everything to work onto this machine. Down at the bottom, there are stacked HBMs, which communicate through the on-chip network and drop data either into the CMEM or directly into the vector memory. So they obviously each have an HBM controller. Over here on the left, there's a chip manager or sequencer that talks to the interface and the PCI Express, which goes out to the host. That's how the data comes into the machine off of a host. And then over on the right, there's a router to the interconnection network, and that goes to the 6 different 8-bit transceiver lanes which go to the other 6 chips around it in the three-dimensional torus. And I'll show some more pictures of that in a minute. So here's the, again, going through the pieces. The fast map mulls, convolutions, transposes are done in the matrix multiply units. The DRAM gives lots of in-package RAM. In this, there is 32 gigabytes of in-package HBM. And being HBM, it's high bandwidth. Here's the chip-to-chip connections and the chip-to-computer connection over PCIe. Here's the stats. I'm not going to go through all of them, but a couple of the highlights. As I said, it's a 7-nanometer chip. The previous generation was on 16 nanometers. It's a little bit smaller than the previous generation, and it's also lower power than the previous generation, but has higher flops. The processor clock rate is slightly higher than the previous generation. Most of the additional flops come spatially from more matrix multiply units. And in V4, we're at 22 billion transistors. I'll cover some of the other things. I mentioned the memory, 128 megabytes of CMEM, 32 megabytes of total VMEM, that's 16 megabytes in each of the cores, and then 10 megabytes for the Sparse Core memory. I'll be talking about Sparse Core a little bit later on. As in now. So the Sparse Core is a special processor inside of the TPU, which is there to process embeddings. Embeddings, you can look at as a sparse matrix multiply, or you can think of it as a lookup table for data. If you think of it from the point of view of something like an ads processor, embeddings are where the data is stored, that this person is in this geography, or this person has previously done this other ad search. Something that's very sparse because it's going to be one-hot represented for all the different geographies and things like that. So this is something that's very inefficient to do in a dense matrix multiply because you're doing a lot of multiplying zeros by zeros. So what the Sparse Core does is it's an accelerator inside of each of the TPUs, which is there to do 2 things. The first thing is it does a lookup into sparse memory. And the second thing it does is it fetches that memory from other TPUs in the system. A typical recommendation system with what we call large embeddings has really large embeddings. It completely swamps the 32 gigabytes of HBM. And in the case of training, we will want to run this on 4,000 or so different chips, and we'll want to be able to pull embeddings from all of those different chips. And that's done over the IC on network and orchestrated by the Sparse Core. So this gives you massive parallelism of memory, and it allows you to shard all of the embeddings in a model parallel way across all the different chips that are out in the system. The architecture of the Sparse Core is relatively straightforward. It looks like a processor. It's got its own memory, and then it's got fetch and vector operations and flushing. Then it's going to be able to concatenate embeddings. If you do a lookup for 4 different embeddings, you can concatenate those together. The Sparse Core performance, the whole purpose of the Sparse Core performance is so that we can process embeddings much more quickly than either a sequential processor like a CPU or a dense matrix multiply unit like a tensor processor, Tensor Core. And so here, the version for Sparse Core, there are 128 of the Sparse Core engines on the device, and those can get 30x the performance of a CPU and can also get significantly higher performance, 3x higher performance than on the previous generation TPU V2. So if we take those and build it out, let's start with the rack. So the architecture of the V4 device is 4 chips on a tray, 2 trays with each CPU, and then 16 of those trays put together into a rack for a total of 64 chips in a rack. And this is a picture of the rack. Each one of these is one of the trays with the TPU or the tray with the CPU host. There's copper inside the racks to do the interconnection networks. From rack to rack, it switches to optical interconnect between the chips that are on different racks. And then obviously you've got power in and heat out. In addition to the interconnection networks that are directly between the TPUs themselves, the CPU obviously requires communication, and that's done by data center networking, also known as Ethernet, which connects the host CPU to the outside world within the data center. Zooming in on the board, as I said, there's 4 TPUs per board. Here's 1, 2, 3, 4. The cables shown here are the water cooling. So there's 4 cold water come in and then hot water goes out. This is similar to how fans work to cool your device in an air-cooled system. It's just much more efficient with water cooling, and you can keep the junction temperature significantly lower, which allows us to put more computation into the device without being worried about thermals. PCI Express is Gen 3 by 16 from the TPUs to the host. And the on-chip, I forget that, oh, there it is, octal small form pluggable connectors are where the optical cables connect from these 4 chips to other trays of chips in the system. And each of these supports 400 gigabits in each direction. This is the entire system. The system we call a pod, and it consists of 64 Google racks deployed in 8 groups of 8. So there's 8 by 8 racks of 64 chips for a total of 4,096 interconnected chips without touching data center network. So in this generation, you can take and you can spread a training workload over 4,096 chips, and all the communication between the different workers in the system occurs over the high-speed SerDes ICI network. The total compute is more than 1 exaflop in one of these systems, and each of the systems, this is one system of 8, has a CDU, which is a coolant distribution unit, and several other different types of infrastructure blocks to manage the entire system. There are well more than dozens of these systems deployed. I'm borrowing these slides, so I'm not going to ad lib and add the numbers, but it's a lot more than dozens of these systems. This is fully productized. There are no more of these systems being built anymore. Only version 5 and beyond are being built. This is zooming into the 3D Taurus. So the organization of the interconnect is based on a building block, which is a 64 chip 4x4x4 cube connected with the 48 optical interconnect switches. So this is an example over here of a 4x4x4 cube. And you can see, if I pick this example right here, chip number 220 connects to its north, south, east, and west neighbors, along with one neighbor inside the cube, and one neighbor, in this case, dangling outside the cube because it hasn't been connected to anything yet. When you build the 4,096 chips, you will end up with an entire 3-dimensional torus of those chips. The connection outside of that 4x4x4 cube is done with an optical circuit switch, or an OCS. This is a connectivity via mirrors and lights on the optical fibers. It is set up at the beginning of the job's slice allocation. And what that means is if I want to run a training job that has only a single 4x4x4 cube, what the optical switch does is it connects wraparound links in the previous diagram. So I don't have a good one here. This one right here, that uplink will actually come in the bottom and connect to 303. This link over here, 333, will be connected to wraparound and come back to 033. If I want a 4x4x4 cube, because that's the size of my training job. If I want a larger training job, then we have butt 2 cubes logically together and then connect a 4x4x8 configuration, etc. there's no switching of packets in the optical circuit switch. This is just literally a circuit switch network done by optics. This is better for power, but it's really better because we don't add any latency and congestion that we would get in terms of a normal switch. Looking into the fiber itself, I'm always amazed at how Google organizes everything in a data center. Everything is labeled, everything is color-coded and organized, so you get nice pictures here. There's more than 16,000 individual fibers being connected in one of these 4,000 chip pods. And if you add up all that fiber together, you can circle the state of Rhode Island. And one of the reasons for all of these labels, as well as the optical chips and all of the plugging nature of everything, is so that it's deployable and serviceable. If we get a bad DRAM on one of the CPU trays, we want to be able to just have somebody walk in, pull out the tray, and plug in a new tray and reconnect things. If we get a bad TPU tray, we want to pull it out, unplug, and replug in the optical connectors and be up and running a couple minutes later. So here's the physical system of the optical interconnect. So here's 64 racks shown over on the left and all the different fibers coming out of them. These fibers are interspersed. You see that each of the racks contributes one of the red colored fibers and one of the yellow colored fibers, etc. These go into the optical switches. There's a sort of carefully constructed set of switches, set of connections within the optical switch, such that we can always connect whatever the person wants. So if the user wants an 8x8x4 or a 4x4x12, and yes, sometimes there's a reason for a 4x4x12, that can be constructed out of the optical circuit switch. And as soon as you instantiate your training job within the data center software, it will do that configuration for you and then launch the job. One of the reasons for the optical switch is to deal with reliability at scale. You can make a system as reliable as you want, but you can never make it 100% reliable. There's always going to be things that are down. You get a bad DRAM, you get a bad HBM, you get a bad chip of one sort or another, a fan breaks. And one of the reasons for having this optical build out is so that we can have, this is a set of logical 4x4x4 cubes, and we have, in this case, 2 of them are dead. And the blast radius of one dead chip is one of these 4x4x4 cubes. We can ignore that and build the pool of whatever somebody wants without those 2 dead 4x4x4 cubes, and build it, and it'll be contiguous and completely connected. So in this case, what's shown over on the left, with this cube being dead and this cube being dead, we can still build this 8x8x4 out of the yellow cubes, an 8x8x8 out of the blue cubes, and a 16x8x16 out of the purple cubes, leaving the 2 leftover broken pieces to be repaired. This is of a significant advantage, because in older generations, when we first started building these, they would be hardwired together. And if one cube is down, you have to deal with things like routing around. So you're doing an all reduce, and the algorithm will have to route around this broken chunk. And you don't want to be doing things like that. It both adds latency and runtime to the training job, as well as frustrating the users who get things that aren't nice powers of 2. This is a little graphic of the slice availability. If we pretend the OCS optical switching doesn't exist, this shows that as you ask for larger and larger worker pools or slices, the availability goes down. So probabilistically, as you have a failure rate of, say, success rate of 99.5% or 99.9%, meaning 99.9% of chips are up. Even with 99% of chips up, if you ask for a slice of size 2000, your availability approaches 0. However, with the OCS and the ability to reconfigure, we can maintain well above 50%, even at slices of size 2000, being requested. And since most of the slices people ask for are down in here, we're getting extremely high reliability in offering those slices to the customer in the data center. Switching gears a little bit to how workloads are progressing in machine learning. For TPU V1, which was 2016, back when we were doing inference, most jobs were a standard multi-layer perceptron with a mixture of these DLRM models being a multi-layer perceptron with embeddings attached to them. 61%, 29% was RNN, that's basically DeepMind playing chess. And then 5% CNNs for your Google photos and things like that, and transformers hadn't been invented yet. If you zoom forward to what is going on the TPU V4, this chip was productized earlier than 2022. It was productized back in 2020, but it was data sampled in 2022. We're down to 24% being MLPs and embeddings models. 57% of models are now transformers. Those break down into 26 of the 57 being BERT-based models and 31 of the 27 being large language model. And those, if you haven't noticed, have really taken off in the last 2 years. So this number is an underestimate of what's going on in the data center today for large language models. One of the things that we want to aim for with that three-dimensional network is scalability. For standard models, this is actually not looking at large language models yet, but it's got some BERTs, but not super large models. We get nearly perfect scaling over the ICI, with the exception of embeddings models, which do lose some of their oomph as they get spread larger and larger because of that model parallel sharding of the embeddings. So the embeddings start being farther and farther away, and the size of the cut through the interconnection network from left side to right side, which is the metric of how quickly the embeddings are being processed, starts to tail off as you get beyond 1,000 systems. But all of the other types of models will continue to scale nearly linearly. This is because the all-reduce is not a huge portion of the total amount of compute, and it can typically be hidden behind the compute on the dense layer MLPs. So this is just kind of recapping a couple of the features in the TPU Before. So we're getting 10 to 1,000x efficiency over competitive solutions, being things like CPUs or something like that we would otherwise do these kinds of models on. Some of the principles of the entire system, we build a specialized hardware for dense matrix multiplication. You can see from the architecture of the TPU, it's not really a sea of processors. It's intended to be an MLP wants to do a big matrix multiply, so we're going to give you a big matrix multiply. And that's how we're going to do matmuls and convolutions. DRAM is high bandwidth memory, stacked and connected 2.5D between chips over low profile bumps, as opposed to having pads for something like an LPDDR DRAM. Specialized hardware for scatter, gather, and sparse operations. That's the Sparse Core that I mentioned before. The optical circuit switching is for two things. It's for both fault tolerance, and it's so that you always get a 3D torus no matter what size you build. We do support specialized data, including int4, int8, and BF16. No bonus computation for int4 in this generation. And as I said earlier, liquid cooling, so that we can stuff as much computation as possible onto the chip. So a couple of slides on how we build it, which is really a little bit more related to my job in the world. First of all, a couple of metrics. The primary metric that we typically look at in designing a machine learning accelerator system is perf per TCO, or perf per dollar. TCO is the total cost of operation of the product, and that basically divides into two things. One's the CapEx and one's the OpEx. CapEx is the cost of the stuff. It's the chip, the fans, the boards, the racks, the data center network infrastructure, the CPUs. It's the bill of materials that goes into building the chip. The OpEx is how much it costs to run the chip. It changes over time. Currently, we use 6 years operational. So basically, this is the cost of power for 6 years. From the TPU program's point of view, power is always an OpEx, even though from somebody else's point of view who's building a data center, power divides into a CapEx and an OpEx. But anything that supplies power onto the TPU is considered an OpEx. So when we're making decisions, we can say, well, this particular decision allows the chip to benchmarks our workloads as 2% faster, and it costs us 2.2% more power. Well, power is not the entire cost, so 2.2% more power is probably worth it to get 2% higher performance. I won't give the breakdown here, but you can imagine there is a breakdown, and that means there is a magic crossover point from when we will be willing to spend more power to get more performance. Obviously on CapEx, if it's something like adding a new feature or say increasing the size of the on-chip SRAM, we can do a direct calculation. In the simulator, we can decide how much benefit we get out of that additional on-chip SRAM in terms of performance, and we compute its cost, and we can do a cost benefit on which is better. And it all comes down to this one equation, perf per dollar. If it's inference, we do care about latency, which is raw performance, and that will fit into the metrics as well. But as a general rule, perf per dollar or throughput per dollar that is spent is the primary metric. So CoDesign is the word that at least used within Google to talk about co-designing the hardware with software simulators, which basically means architecture development in the FPGA context. So we basically have a circle. We want to do work on existing systems to accelerate workloads. So this is restructuring the workload, maybe change your batch size, change what kinds of operators you're calling, basically improve your workload with the hardware you get. That generates things like bottlenecks. Once we know what bottlenecks are, we can try to make proposals for next generation architecture systems. We can evaluate those through perf TCO and simulation and do various different sweeps, the same way that in an FPGA you would sweep across how many wires or what the length of wires are or what your muck structure is. We can simulate across different pipes of speeds and sizes that exist within the hardware and optimize for the next generation of chip. This allows us to enable a new capability, which then of course has to be implemented onto the end models so that we can use it, and then we go back around the circle again once we've put out the next generation hardware. So I mentioned the speeds and feeds. So this goes back to the block diagram shown earlier for the TPU Before. So shown in a little different layout, we've got the 2 tensor cores right here. The primary metrics that reflect performance here are in the MXUs, how many flops do I have? In the VMEM, how much capacity do I have? And what's the speed at which I can load and store from that vector processor from the tensor core itself? There's also the cross-lane units, which are used to do transposes and anything else which requires manipulation of the tensors. Then we have a bandwidth between the vector memory and the on-chip interconnect and the CMEM. You also have the high bandwidth memory out here. The high bandwidth memory bandwidth is definitely a key parameter for how fast the system is going to run. If you add too many flops and you don't support it with enough HBM bandwidth, you'll be throttled by the amount of memory bandwidth that you can use to get data on and off of the tensor core. There are other operators in the system, which we'll just call other. There's the bandwidth to the ICI, the bandwidth between the HBM controller and the memory, the PCIe bandwidth, the host flops, because some models have to do work on the host. So you can think of JPEG decoding or encoding being done on the host. You can think of pre-processing of embeddings data. In the case of inference, we do embeddings themselves on the host. And then the DRAM capacity and bandwidth for the host's DRAM and the networking going out on Ethernet into the data center. These are all the different speeds and feeds that we can play with. And then it's not really shown, but you can also play with different vector instructions. You can come up with a whiz-bang new vector instruction, and then the simulator can try to evaluate the amount of performance that comes from that. And this is an example of how the simulator works. So our simulator is called TFSim, or TensorFlow Simulator. It takes as input a TensorFlow graph. If you're not familiar with TensorFlow graphs, it's just a data flow graph that represents the computation that you wrote in the TensorFlow Python. It's shown as a graph of operators. In this case, there's a batch matmul, which is 10 by 4 by 1024. That's n by m by m by k, m by k by k by m. Then it has to do a vector operation, add, a ReLU, a reshape, and then that goes over here. What the TensorFlow Simulator does is it walks along this graph. At each one of these nodes, it does a simulation of how much time that operator is going to take. You can do multiple different cost functions or models for computing the performance of a different piece. For example, you can do a simple roofline, and all that says is compute how much time is going to be spent pulling things on chip from the HBM, and compute how much time I need to do flops and do the max of those, and that will give you your roofline performance. It's idealistic because you could also be spending time in the vector processor. You could also be spending time preparing data or doing a transpose or something. So there's a detailed cost function which does much more of a simulator. It actually, you can think of it as doing a multidimensional roofline, because then we take into account all of the different elements in the system, such as the vector processor and the cross-lane units, and compute a multidimensional roofline, which will become more and more pessimistic the more things you model. That's where we would model things like padding. So the matrix multiplies are nominally 128 by 128. But if you give it a 96 by 128, there's going to be zeros there. And the TensorFlow Simulator wants to simulate that logical tensor has to be padded to get to a 128 by 128 matmul, and we have to take that into account in the performance. Other decisions that are being made by the simulator here: when I do a reshape, is that free or do I have to do work? And that's an element of how did the previous operator choose to store the result of the computation? How did the compiler of the previous operator choose to store the computation? Did it store it in a transposed form or in a non-transposed form? Did it store it in a way which is easy for me to read and generate a new shape of tensor? Or do I have to do work using the vector processor and the cross-lane unit to reshape that tensor into a different shape? This basically gives us the equivalent of a VPR in TPU architecture, because we can play around with all the different parameters of the system, run a simulator across many different workloads, and compute that magic perf TCO for a proposed change to the hardware. So moving forward to some trends. This is taken from Jeff Dean's keynote talk at Hot Chips, so I probably can't do the same justice that he did to it, since it's mostly on the ML side of things. But this is basically, over the last decade, we've gone from CNNs, which take a picture and produce the result that this is a leopard. We were multiple years ago doing speech to text, and that takes some audio and turns it into the text. How cold is it outside? With transformers, I mean, language translation was done before transformers, but with transformers, it got a whole lot better. And we can now say, hello, are you, to bonjour, comment allez-vous? And beyond, as you can see from what's going on in larger language models today. And of course, state of the art today is being able to do much more complicated analysis. So in this case, it's a picture, and instead of just identifying this is a leopard or a cheetah, I can't really tell the difference here, but it can actually take the context, and it can say a cheetah lying on top of a car. So this is adding more understanding in addition to what otherwise would have been a simple CNN. We have to show Bart since it's been out for a few months now. These are some examples. That's a picture of Jeff Dean, if you don't recognize him. Some of the things that Bart can do right now. Bart is Google's ChatGPT for anybody that doesn't play around with these things. And Jeff asked, reverse the letters of hot chips and tensor processing unit for me. Bart says, sure, and produces the reverse strings, and then seems to spontaneously offer to do it for you in Python by writing code. And Bart will do this, will just spontaneously offer to write code or something like that for you. And here is written code in Python. And then gives a little speech about the code that it wrote. And then asks if you want to talk about anything else. This is really cool technology. One of the interesting things that's also true about it is it's very expensive technology. Unlike that simple CNN recognizing cheetah, I can't speak about the exact size of Bart, but it's bigger. It runs at lower batch size, and it runs on multiple chips to do these kinds of things. Whereas something like that simple CNN mentioned back here might run batch size 32 on a single chip. So the demand for compute is growing exponentially. You've seen exponential pictures many times before. This is just showing it with a bunch of sample models from GPT-3, which was trained over the last year or two and announced last fall. Here's Palm, which is one of the models which goes as the input into the spirit of Bard. We're on about a 10x per year trajectory. For people that build hardware, you can look at this and say, well, that's not going to happen. We are not going to build hardware that's 10x more performant every generation. So the world has to come up with better ways to do this. We can pay more for hardware and then hopefully charge more for the output of that hardware. But there are other techniques that are taking over today. One of these is to, instead of making a separate model for each different type of task, so I might have a language translation task, a facial recognition task, and some kind of a recommendation system. And 3 or 4 years ago, we would have had all of those as being different tasks. They would have been completely different machine learning models implemented in TensorFlow. Some of them run on chip A, some of them run on chip B. One of the trends that is happening right now is to join all of these together into a single task. This also allows them to share common pieces of their structure. They can be connected together over, I don't think I'm going to go through pathways, but there are some papers on pathways, if you Google it, that talk about how to connect different models together, even though they look like they're not doing the same thing. And you can see this is showing some sparse activations of those models as they share some of their computation. This is a way of blunting some of that 10x growth. The second thing is sparse models. So dense models is your standard multi-layer perceptron. Every layer is fully connected and connects to the next layer. Sparse models do all kinds of different things. They can be applying sparsity in the sense of not all of the tensors are full. There are techniques such as you compress every adjacent set of four adjacent memory words, and you condense them into one with a tag saying which of the 4 words is the correct word and which of the other 3 are zeros. And this is a 4x compression in the size of the tensor. You can take advantage of that in hardware and also in memory storage and memory bandwidth. Other types of sparsity are using things like embeddings, and other types of sparsity would be doing things like mixture of experts. Modality, in addition to what I was showing before, which is different types of tasks, you can also take different types of data. So on the left, you can take images, text, sound, and video. You can combine them together into a model which takes all 4 of those types of inputs and produces an output. And those would be multimodal models. The other thing you can do to blunt that growth in cost is to not always serve that extremely expensive model to everything. If you take the example of Google search, Even though you see things like Bart being built into Google search, a lot of Google searches don't require Bart. If you go to the Google search bar and you type in 5 times 12 because you just want literally to know what 5 times 12 is, we don't need to call a large language model to figure that out. That can be figured out by standard web answers, which is technology that's been around for a number of years and is not incredibly expensive. So one of the ways that you can make large language models feasible is to run the giant model on 1% of the data, maybe run a medium-sized model on 1% of the data. 8% of the data gets a large model, and then 90% of the data runs on a tiny model. And this is a way of amortizing your overall costs so that everybody gets what they want out of their query without everybody having to pay the cost of things that they don't really need. So looking at scale, large language models and scale, the most important thing, you'll see especially lots of startups saying, we do LLMs, here's our chip. That's not very useful. You can't do an LLM on a chip. You need a system. So you need to have workload-driven features. You need to be able to scale thermally, and you need to have a system that scales to thousands and thousands of chips for a single workload in the case of training, and scales to tens of chips, to hundreds of chips in the case of inference. You want to be able to do data center level power and power management. Power is the most important variable that exists right now. We can add more flops to the chip. The question is whether you can pay for adding those new flops in terms of power. So being able to balance power in the data center system is critical. I already mentioned resilient computing, which comes from being able to do things like reconfigure the interconnect, and then dealing with errors so that you can get both hard errors where you have to do things like reconfiguring, but also softer or transient errors so that you can deal with errors that occurred in the system and keep on moving. So I'm going to skip a couple of slides so that we have time for questions, but I'll skip by going more quickly. Some of the things that we want to be able to do are to have power-aware scheduling. Once we know the arrangement of all of the different tensor processors and racks that exist in the system, we can track the amount of power that different type of workloads are running, and we can balance them so that across different bus ducts or power supplies in the data center, we can balance them to minimize the probability that anybody ever gets throttled. And it also then allows us to control the power that's going on in different data centers, and we can fine-tune, we can introduce turbo modes, we can produce more reliability-based data center statistics, how long has this chip been running at a given power, etc. We can also use this to, when we do have to throttle something for power delivery reasons, we can do so on background or freebie jobs rather than doing on a job which is important. Silent data corruption is, this can be anything from soft errors occurring on memories to any kind of a setup hold violation occurring as a result of environmental issues. They're a real problem in hardware. You don't see them in small scale hardware. You tend to see them as you scale. And one of the things that we want to be able to do is catch those errors and keep on moving. To deal with the silent data corruption as if it's a dropout in a computation, a dropout in a machine learning network, and just keep on moving and compute the right result anyway. So this is a topic that is of internal research. This is an example of ICI and data center network working together. So here are a bunch of different sets of 4x4x4 cubes, and we want to train Palm 540B or 500B, which requires these green 4x4x4 cubes to train. We can use the optical compute network to select a number of cubes from our data center, connect them together, and go off and train Palm. And I'm going to close the discussion part with a video. So this is an example of Palm training in the data center, and the model being consistently moved around onto different 4x4x4 cubes for one reason or another. It can be moved because I've done a checkpoint and I'm going to bring it back, and the scheduling system needs those cubes for something else in that particular place. So it's going to move the Palm data center work to another chip. This is going on in days. So I think this is like 50 days long to do this training. And this system has to be able to run for 50 days. It's constantly doing checkpointing. Whenever it gets an error, it reverts to the previous checkpoint. It's moving systems and cubes around. It's making room for other jobs. It's prioritizing based on the priority of different types of jobs to make sure that everything gets done, and all being orchestrated by the data center software. And that's all I had prepared. Oh, it's going to keep doing the video, but I'm happy to take questions for the rest of the time.